Hello students, welcome to this lecture. So in this video we are going to discuss about the memory management techniques. Normally the memory management techniques for embedded systems is required that if any embedded system requires operating system to be operating that particular system, operating systems have some of the modules which deals with this memory management. So in those memory management techniques, two techniques are very important that was given in our syllabus are virtual memory and the direct memory access. So we will discuss one by one. So first one is virtual memory. Virtual memory is a storage allocation scheme in which secondary memory can be addressed as though it were the part of the main memory. So virtual memory is required for an embedded system comes from that if that particular embedded system have secondary memory. Secondary memory means we can imagine it as a hard disk. So the size of the hard disk is very large. Also the price of the hard disk is somewhat less. But if you are comparing with the RAM or physical or main memory, physical memory, so that particular physical memory is coming with RAM. So the RAM devices are eventually costlier. So making the RAM devices as big as possible is somewhat making our embedded system to be a costlier one, because the RAM devices are costlier. So if you increase the device size, then our system will also be going to be costlier, so that we cannot sell our system. So in order to making that into our trade-off, we need to have that particular physical memory as a very compact one. So we need to have the hard disk size can be a bigger one, but the physical memory can be a smaller or a compact one. So but the system's speed is going to be traded off between this cost and this system memory. So we need to choose a particular physical memory as somewhat compact size, but eventually whenever we are selecting that particular physical memory as a compact one, but the speed is going to be reduced. So in order to making that particular system to be speed, we need to have the virtual memory. So what is the virtual memory is? Virtual memory is an imaginary memory part where we are having the copy of the hard disk files into that particular virtual memory. But if you are having that particular hard disk file is going to be copied into the main memory, then that particular main memory have to have some address, because the file which is in the hard disk it will be in one address, but if it is being copied into a physical memory, then its address will going to change. So that address translation is very much important. So that address translation can be done with the help of the main memory map to the virtual memory, so that we can have that particular hard disk file is going to be copied into the physical memory, and after the processing and after the program is being executed, the file may be getting updated. So updated file can be copied into the hard disk. So this kind of operation is going to be called as virtual memory. So this scheme has two advantages. One is it allows us to extend the use of physical memory by using disk. The second one is it allows us to have memory protection, because this particular system is going to have memory protection, so that we may not be getting corrupted with the processes which is in between the physical memory and the hard disk. So it protects our memory, because each virtual address is translated into the physical address, so that we may not get any corrupted file at all in between our processing of the data. So the basic virtual memory methods are going to be two. One is segmentation, another one is paging. So what is segmentation? Segmentation is a division of the memory space according to the need of the application processes. So the segmentation is a division of memory segments with variable page lengths. So the memory is going to be segmented. It is going to be divided into required amount of segments, so that we can use that memory into data. For data, it can be used for instructions, it can be used for stack, and it can be used for heap. Heap is some particular memory segment where we are being stored with the static variables and the dynamic variables. So those variables are going to be dynamic in nature, and they can be updated in while you are running the program, because after program is going to be executed and finished, those variables are being updated and those variables are being stored in the physical memory, and that copy is going to be eventually copied into the hard disk too. So in order to having that particular segments, in order to keeping track of that particular segments, and in order to keep track of stack and the heap, we need to have a segment table, because that segment table will be having base address and the limit also. So that segment table having that base address is going to be the starting address of any segment. So the limit is going to have, that is the base, it is going to have the length of that particular segment. So this length is going to be variable in nature. So depending upon the length, that particular segment is going to be allocated, and that particular memory can be used for the embedded systems. So the next is going to be a paging. Paging is a division of physical memory into fixed size of blocks, because in the segmentation we have divided the memory segment into variable size, but the division of the physical memory with a fixed size is going to be called as pages. So typically page may be having from 4 KB to the 16 KB, and the virtual address is going to be calculated, because for a given page we may be having a virtual page address and the virtual page number. From that particular page number, if you are adding a particular offset, then we can address a particular variable with its virtual address. So the virtual address is going to be virtual page number plus which offset bits, and the physical address can be translated from this particular virtual address by making some of the calculations, that is a translation calculations, that is out of interest to this particular video. So the translation calculation will be made, and the virtual memory address is being updated into the physical address, so that the given particular data can be stored inside the physical address. So the page map is very much important, because page map will be giving the detail about the particular virtual address and the physical address. In this particular scenario, we can also have look into this particular diagram. Here we will be having our hard disk, and this will be our physical memory. So whenever we are executing our program, we will be executing in this particular physical memory only. So whenever we are executing, suppose if we don't have a particular data inside our physical memory, means you have to be copied from this particular hard disk. So it will be copied from this hard disk, and the address of this particular hard disk address is being copied into this particular memory map. So from this memory map only we are having the visual memory calculator. So this page translation calculator will translate this particular hard disk the address into a virtual address, and that virtual address is going to be copied into this particular physical memory, so that our particular hard hard disk page is being copied into this particular physical memory. So after getting that program has been executed, the variables will be updated. So after updation of the variables, that file is going to be copied with the help of the address which is being translated in this memory map. So it is being copied into the hard disk. So this is the process where we will be having our paging. So demand paging is on the same idea, that is whenever we are having a particular page is not being available in a physical memory, means that is being given as a page fault. So if that page fault occurs, then the processor will do that, it will be set as a page fault. So it fetches the missing page from the disk into the RAM. So the memory address is going to be adjusted by using the physical memory table. So using that particular table, the address will be updated and that particular data will be copied into the RAM. So this is all about the virtual memory. So this is all about the demand paging, which is very much important in case of large scale embedded systems. So the next is going to be the next memory management technique, which is being called as direct memory access. So this kind of direct memory access are very much practical in the SATA or the parallel or the serial port communications is made between the memory and the external devices or memory and the processors. So this is a common technique which is being used in our computer systems. So what is DMA? That is the direct memory access, is a process of communication for data transferred between memory and the input output, controlled by an external circuit called the DMA, because this DMA will be controlling the data flow between the memory into the processor. So the memory and the input output devices, the process of that particular data transfer will be controlled by the DMA but not by the processor. So why it is not by the processor? Because the processor is a master. No. So why the microprocessor don't take that particular responsibility, means because the microprocessor will be having some other works to do that may be important. So the memory cycles, so the operating cycles of a microprocessors need not to be wasted at all. So we will be having a separate DMA controller which controls the data flow between the memory and the input output devices. So how it will do means, here we will be having in our microprocessors that hold and the hold acknowledgement pins. So these two pins are being connected with the DMA controllers with the bus request and the bus grant pins of the DMA controllers. So what it will do is, whenever input output devices needs some memory content, it will be intimating into the DMA controller. So the DMA controller will give the bus request to the microprocessor. So that bus request will be given to the hold pin of a microprocessor. So this hold pin will be getting into the higher logic position. So that will be given as 1. So by giving the 1 to this particular hold pin, the microprocessor will stop its execution. So whatever the instruction it is running, it will be stopping that particular instruction and it will be giving hold acknowledgement to the particular DMA controller, because the stopping of this particular process will release the address and the data bus of the microprocessor. So at the time of leaving, it will be giving the hold acknowledgement signal to the DMA controller. So if the microprocessor releases the address and data buses, then that will be open to usage of the DMA controller. So upon getting this hold acknowledgement signal on the bus grant signal in the DMA controller, the DMA controller will be taking the control of the address and data bus. So after getting this particular address and data bus control, the DMA controller will be giving the address, so the memory will be giving the data, so that data transfer will be available from the memory to the DMA controller to the input output devices. So after this particular data transfer is being finished, the hold pin will be getting released, so this hold pin will be getting into the 0. So after this particular direct memory access is being completed, so this hold signal will be getting released, it will be getting into 0, so that the microprocessor will be having regaining this particular address and data bus access.